Welcome to this introductory video on plotting data in R using ggplot. So R is extremely powerful at plotting data and generating high quality, highly attractive graphics. And there are three main plotting systems in R. The base plotting system, which comes with your R installation. You don't need to add any packages to use that plotting system. The lattice plotting system and the ggplot plotting system. And for this video, we're going to focus on ggplot because arguably it has become the most popular package for plotting data in R. A lot of other tutorials for plotting data in R will tend to give people a bit of a grounding in base plotting in R first, because traditionally that was the way that people used to plot their data in R. But actually, I am of the opinion that there's sort of no point really in spending time learning how to use base plotting in R when you can just sort of jump straight into ggplot, which is much simpler to use, much more intuitive, and produces much more satisfying graphics. Before we carry on, I would highly suggest that you have already watched through the introduction to R video, at least just the first part, so that you have a decent understanding of how to navigate RStudio and how to do some basic data exploration tasks. So before we start, ggplot doesn't come with your base R installation, so we need to install the package just like we did in the introduction to R video. So you'll remember that the way we do this is by using the function install.packages. And then the name of the package is actually ggplot2, and then hit Control Enter, and then RStudio will download the information from the internet and install the package for you. And while it's doing that, if you remember that we can also do this by going to Tools, Install Packages, and typing ggplot in here, and RStudio will do that for you. So as we can see, it says that R has finished downloading and installing ggplot for us. Because we still don't have access to the ggplot functions until we have loaded the package into our memory. And the way that we do this is by calling the library function and supplying it with ggplot2 and hit Control Enter. And so to explore the package a little bit, we need an example data set. And handily, R and many R packages come with, there are dozens and dozens of data sets available to us. And throughout this tutorial, we're going to explore a very famous data set that is available in R called the iris data set. So handily, if you want to explore which datasets are available for you to use freely to practice your plotting or data analysis skills, if you just run the data function without any arguments, then R will return a list of data sets that you can load into your current R session, explore them, plot them, analyze them as you want, which is a good way of practicing some R skills. And so if we want to load the iris data set into our current working R session, we again call the data function and supply it with the name of the data frame that we want, which is iris, and hit Control Enter. And as you remember from the introduction to R video, we've got this useful command head, which will just show us the first 6 entries for the iris data set. So you can see that this iris data set basically has measurements of sepal length, sepal width, petal length, and petal width for, you can't see it here, but for 3 species of iris. And so if we call the summary function, we can see some summary statistics for each of these continuous variables, and we can see that we have 3 levels of our species variable, each containing 50 different individual iris plants. So let's start to explore our data graphically. So as part of the base plotting system, we have this function that we came across in the previous video, just called plot. And if we supply the name of the data frame to this function, and then basically we get a plot of every variable against every other variable, which is a very nice way of exploring quickly and seeing if there are any relationships or patterns in your data, provided of course that you don't have a data frame that has a large number of variables, because it becomes very difficult to read. And so actually this is a good time to mention that there is a difference between producing plots for the exploration and understanding of your data yourself, and the production of high quality, attractive and clear plots that convey the information that you're trying to convey to your readers. And so the plot function is quite a nice way of producing quick and dirty plots that show you relationships in your data, but are not necessarily the scrubbed and cleaned plots that you would end up putting together in your thesis or for a publication. So looking at this plot, it looks to me as if there's an interesting relationship between petal length and sepal width, and we can see that we have a pattern in our data where it seems that we have two different clusters of data points. So we may want to explore this a little bit further. So again, we can use the base plotting command plot and supply it with two variables. So we can supply it for the x, iris, and the column petal length, and on the y, iris, sepal width, and hit Control Enter. And then we find that we've just got sort of a zoom in of that individual plot where we have petal length on the x-axis and sepal width on the y-axis. And we can see that it seems like we have two large clusters of irises. So let's plot some of this data instead and have a look at this relationship using the ggplot plotting system. So the GG in ggplot stands for the grammar of graphics. So the grammar of graphics is a school of thought that says any graphical representation of data, any plot, any graph, can be produced from a series of layers. So, for example, if we start with a plotting area, so you imagine this is your sheet of graph paper, so at the moment we have just a plotting area where our data will eventually go with a series of grid lines that have been plotted. Now on top of this base plot, we can layer our axis ticks, we can layer the values for the axis breaks, we can layer on top our y and x axis labels and a title for our plot, and then we can layer geometric objects, or geoms. So what I mean by a geometric object is a shape. It could be a circle, a line, a square, a box, or text. Some sort of way that your data can be represented. So for example, at the moment we've got point geoms. So we've got dots to represent an individual observation in our data. We can add additional geoms, so they could be box plots, regression lines, confidence intervals, text, and we can keep going and layering on top to produce whatever plot or outcome that we desire. Of course, this particular plot is not ideal and is quite messy and hard to understand, and isn't the sort of plot that you would end up publishing, hopefully. But it illustrates the point that you can continue layering geometric objects onto your plot to convey the message that you want from your data. And this is the way that ggplot functions and allows us to create very dynamic and attractive plots very simply, so in a sort of step-by-step manner. And so that's what we're going to do with our iris dataset. So the main function in the ggplot package that we'll use is handily ggplot. and this function needs, at a very minimum, 2 arguments. It needs one argument that is the data frame that you're going to plot, and this is, in this case, of course, iris. And then its second argument is actually a function called AES. AES stands for aesthetic mappings. And this is a concept that is perhaps a little bit hard to get your head around at first, but is actually quite intuitive. So an aesthetic mapping is a relationship between a variable in your data set and an aspect of the plot that is going to visually convey your information to the reader. So, for example, an aesthetic mapping could be the values of the x-axis. So you could map the values of petal length to the x-axis, or you could map the sepal width to the y-axis. So the y-axis is another aesthetic mapping. Additionally, the color of your data points is a mapping. You can have your color depend on the value of a certain variable. The size of your geometric objects, of your data points, can be mapped to a certain variable. Even the transparency can be mapped to a particular variable in your data set. So that's what we mean by aesthetic mappings, and we'll be exploring these throughout the video, so that if they don't make sense right now, they will make sense by the end. So if we want to recreate using ggplot, the plot that we created in base graphics a second ago, where petal length is mapped to the x-axis and sepal width is mapped to the y-axis, then we simply need to supply the x and y aesthetic mappings inside the AES function. And we do this by just naming the aesthetic mapping, so x, and then telling ggplot that this is going to be equal to petal length. And notice that whereas with base plotting we had to supply the name of the data frame, use the dollar operator to tell R that we're selecting a column, and then give the column name. With ggplot, because it's already asked us for the name of the data frame, we don't need to do that anymore. We just supply the name of the column, and ggplot knows to look inside the iris data frame for the petal length variable. To supply additional aesthetic mappings inside the AES function, we simply separate them by a comma. And so if we want to supply the y mapping, we just say y is equal to sepal width. And now if we run this function, all we get is, we get a few things. So we get our plotting environment, which is sort of set to the range of the data that we've asked ggplot to plot. We get tick marks, grid lines, we get values for the axes breaks, and we get the column names as our x and y labels. But of course, at the moment, this plot doesn't actually convey very much information about our data, and the reason that is because we haven't yet layered on top any geoms, any geometric objects. And as I mentioned, that ggplot, the way that we plot is by adding layers on top. And this is sort of mirrored in the way that we construct graphs using ggplot. So most of the time we'll start with a base. Think of this as your starting point, your base plot, your graph paper, if you will. And then we can add additional things to this plot by using the plus operator. And now, conveniently, as you'll recall, R allows us to continue a single command or a single function across several lines, and so we can start the next section on a new line to make it easier to read. And we're going to layer on top of this base plot a geometric object, and I think often a good place to start is with a point geom or geom point. And you'll notice actually as we carry on that most of the geometric objects are named in this way, where they start with geom, the geometric object, an underscore, and then a name that's given to that sort of object. And then because these are actually functions, you'll see that they finish with opening and closing brackets within which you can supply additional arguments, so that you can do things like control their size or their positions, etc. And so if we just run this now from we run this whole section of code to produce our plot, and we find that this time we have our base plot with our grid lines, our tick marks, our axis labels, but now we have dots to represent our data. So every single entry in our iris data table has now got a single dot to represent its value for petal length on the x-axis and sepal width on the y-axis. And so you can see that this is very similar to the plot that we created in base graphics a second ago. And so just to recap on that, we've taken our iris data set and we've mapped petal length to an X aesthetic, and we've mapped sepal width onto a Y aesthetic. An important point to make is that there are lots of different sorts of geometric objects that we can layer on top. We'll touch upon a few of them today. But if you come across one that you've never used before, or you're not quite sure how to use, just as if you're not sure how to use any other function, really, you can use the question mark to ask R for a bit of information about that function. So if we do this for John Point, we get the help pane that opens, and it gives you some information on usage. You can see that most of the jobs have a lot of optional arguments, which for the time being we don't need to change to achieve the plot that we want. But what's useful is if you scroll down to this section called Aesthetics, it tells you so it says that John Point understands the following aesthetics. So if you supply in your aesthetics section of the initial ggplot call X, Y, alpha, which is another way of saying transparency, the color, the fill, the shape, the size, then if you supply these, then the geometric objects, the points that you get, will change their shape or size depending on which variable each individual point has been mapped to. And notice that these top two are in bold, X and Y. The reason is that these are obligate aesthetics. John Point won't work unless you've said, unless you supplied X and Y mappings, which of course makes sense because you can't draw a point on a graph unless you know both its X and Y position. And the rest of these aesthetics are not bold, and that's because these are optional aesthetics. You can supply them and John Point will respond and reflect those mappings, but if you don't want to map them, then you don't have to. Okay, so looking back at our iris data set, we remember that we've got these four numeric variables, sepal and petal length and width, but we've also got species, which remember has three levels. So at the moment we have no information as to whether any of these data points belong to whichever of our three species, and it may be interesting to find out whether there's a relationship between perhaps whether this is one species and the other two species are in this population, and so one way that we can get that information is to color each individual point based on which species it belongs to. Let's copy and paste our code so that we don't overwrite, so that you can keep a record of exactly what we code. So we can, if we just paste this here, so we've got our X and Y aesthetic mappings, but we're going to add another one. So remember, we just do that by adding a comma so that we can supply an additional one. And then we're going to supply the color aesthetic. And you can type this in three different ways. You can either type it the American English way, you can type it the British English way, or you can type it the programmer way, which is just by shortening it to col, to save a bit of space. So the variable that we want to map to color is species. Now this is the only change that we're going to make to this ggplot call, and if you run it, we'll find now, a couple of things have changed. So firstly, we can see that each individual point is colored by species membership. And Another thing has happened, which is one of the one of the things that makes ggplot so powerful and convenient, is that automatically it's recognized that we have a color mapping, and it's produced a legend for us, so that we know that red belongs to the Setosa species of iris, green is versicolor, and blue is virginica. And if we add additional mappings, then we'll see that ggplot will create additional legends for us. If you're using the base plotting system, you have to create these legends yourself, which is just an additional step which ggplot cuts out for us. Now we can go further than this. Say at present we're only representing of our numerical variables petal length and sepal width, but let's go crazy. Let's say that we also want to represent on our plot petal width. And one way that we can do this is by mapping petal width to the size, so that the size of each individual dot will change depending on the petal width variable. So again, let's copy and paste so that we can keep track of our code. And again, we're just going to add this under the AES function by separating with a comma. It's the size aesthetic, and this is going to be mapped against petal width. And if we run this, we find that each individual dot, if petal width is large, the dot is large, and if petal width is small, the dot is small. And then again, you can see that for this additional aesthetic mapping, ggplot has created a separate legend for us. So it's not perhaps the best way of representing the relationship between these three variables, well, four variables, but we can sort of see that perhaps petal width positively correlates with petal length, or it could just be actually that the versicolor and virginica species both have larger petal width. Again, we can keep going. There are more mappings that we can play with, so let's copy and paste this code and keep going. Let's say we want, as well as species being mapped to color, let's say we want to map it to shape. So, in fact, let's make this code a little bit tidier by splitting that onto a new line. And we're going to add the shape aesthetic, and this is going to belong to species as well. A word of warning, make sure that if you're going to use the shape aesthetic, make sure that you only map it to categorical variables and not to continuous variables, because if you have a variable with 100 unique values, then you can imagine that you're basically asking ggplot to supply 100 different shapes, which isn't going to give you very much information. So, there's another important point here, that you can actually map the same variable to multiple aesthetics. So here we've mapped species to both color and shape. And so if we run this, now not only are the Setosa irises red and circles, the versicolors are green and triangles, and the virginicas are blue and squares. Now there's a sort of a rule in data visualization that you shouldn't have aesthetic mappings which are surplus to requirements. So what I mean by that is, our species were already denoted by color. The reader gets no extra information by you also supplying different shapes. And in fact, often it can obscure the meaning of a plot. So although you can map a single variable to multiple aesthetics, try to keep it one variable per aesthetic. Now, this plot is becoming very silly very quickly, but let's get even more silly just to demonstrate just what is available to us. And let's say that finally we want to map the sepal length to the transparency of each point. And what ggplot calls transparency is alpha. And so we're going to map this to sepal length. And then if we run this, you can see that the larger the sepal length, the more solid the color, and the lower the sepal length, the more transparent the point. And then again, you can see that we've got this additional a legend that is showing us the differences in the transparency. Another word of warning: transparency isn't a great way of mapping continuous variables. It's not a great way of seeing changes between different values. The human eye isn't very good at picking up or working out what is. I mean, if, for example, it's quite hard for me to decide which of these is 5 and which is 6, for example. So color is generally a much better way of representing differences like that. Okay, so I hope that you understand so far that we create a base plot with the ggplot function. We add geometric objects onto our plot as a layer, and that we use aesthetic mappings to control the way that our variables are represented across our plots. Okay, so we've used the point geom. Now let's have a go at using bar and box plot geoms. So let's create a plot which has species mapped to the x-axis and sepal length mapped to the y-axis. And then we want to plot a bar at each group mean. So we use the ggplot function. The data set is iris. The second argument to the ggplot function is the aesthetic mapping function. And earlier I typed x equals to denote the x and respectively the y aesthetic mappings to cheat a little bit or to make your code a little bit faster, because x and y are the most common mappings that we'll use, and because they are the ones that always come first. So if you remember, you can supply the arguments to a function in the order that they're specified. So we can forget about using x equals or y equals for the first aesthetic mappings. We can just type them, and ggplot knows that we mean x and y. So we want species on the x, and on the y we want sepal length. Oops. That's our base plot, and to that we're going to layer on top JohnBar. And if I don't give any arguments to this, R is going to give me an error, which may not make that much sense at first. It says stat count must not be used with a y aesthetic. The reason it's giving this error is because JohnBar, the geometric for creating bars, means a different thing unless you supply a couple of additional arguments, which we'll do in a second. But it's saying to me at the moment it must not be used with a y aesthetic. So for the time being, let's just remove this sepal length y aesthetic mapping and just see what the JohnBar actually does. So you can see that we've got for each species, we've got a single bar at 50, and you can see here that this is a count. And what this has done is actually drawn a histogram for us of the number of observations in the iris data frame which belong to each species of iris. And of course, this isn't what we wanted. This isn't very useful. But this sort of shows that the base purpose of JohnBar, if you don't supply any additional arguments to it, it's basically for drawing histograms or for showing frequency data. So, for example, if instead of species we supplied sepal width, JohnBar produces a bar for the number of observations in our data frame for each for a bin of values of sepal width. So it is for showing frequency data. Most of the time, the kind of bar plot that we want to show is where the bar is representing some kind of summary statistic, such as a mean or a median. We can change this by changing the stat argument to the JohnBar function. So by default, the stat is count, where JohnBar is literally drawing bars that have the height of the count of the number of observations that fit within a certain range of R value. And so if I rerun this, then the plot is exactly the same. So the stat argument is equal to count. The argument that we want to supply is summary, as we want each bar to represent not just a single data point, a single value from our data frame. We want it to represent a summary statistic, such as a mean. So let's replace this to what we had a second ago with species, and we had sepal length. And so we've told JohnBar that we want to draw a bar at some summary statistic of sepal length at each level of species, but we haven't told it which summary statistic we wanted to plot. And to tell it to do this, we use the argument FunWhy, and this literally means which function of y. Is it a mean? Is it a median? Is it a max? Is it min? And we just say that this is equal to the mean. And so if we run this, then now at each level of species, we get a bar whose height corresponds to the mean of sepal length for each group. Now this plot is so far a bit grey and a bit boring, so let's add a little bit of colour. So if we copy and paste what we've just done, and we're going to add a mapping to colour. But this isn't quite going to work how we think it's going to work. So let's say we want to colour by species, so each bar is coloured depending on, so that each bar is coloured differently. If we run this, a funny thing's going to happen. We find that the bars stay grey, but the stroke, the outline of each bar has been coloured, which, although it looks a bit funky, isn't quite what we wanted. And the reason is that ggplot names things in maybe a slightly unexpected way. So the colour refers to the colour of the border of the jom, of the bar, and the inside is actually called the fill. And so if we run this again, then this time we find that the bars are coloured depending on group membership with these nice colours. You can change the colours, and we'll talk about that in a little bit. Now, there's a difference between an aesthetic mapping, where we map we create a relationship between a variable and some kind of aesthetic, such as colour, and just specifying a single value for a colour manually yourself. If we're creating a relationship between a variable and an aesthetic, we put that inside the AES function. But let's say that we just want all of our bars to be blue. We can let's copy and paste actually, so that we can keep our code for later. Let's remove this mapping between fill and species, and if there are, if you want to make changes to the color, the size, the transparency of geometric objects in a way that's unrelated to variables in your data frame, then you simply do that as an argument inside the function for that geometric object. So let's add a comma. We're going to say that we want the fill to be equal to, and handily in R, you can often just type the name of a color, and if we run this, all of the bars have gone a dark blue. And you'll notice that because color is no longer mapped to a variable, then we no longer have the legend telling us that Setosa is blue or Versacolor is red, whatever. Now, often we want more fine control over our color scheme, depending on how our supervisor or the theme for your thesis is building. And we can do this using color codes that you might get out of your favorite editing software, like Illustrator, for example. And so let's say we have a specific color, which is the color code is something like this. And then if we run this, then we get lovely pink bars instead. So as well as having, if you want to be lazy, you can just say blue without being specific, or you can specifically provide color codes where, if you want to make fine changes, then you can do so. I couldn't even see the difference between those colors actually, but you can make changes using these color codes. Often what looks a little bit nicer is if we add a border to our bars. And again, because this isn't an aesthetic mapping, we just want all the bars to have a black border. We can do this inside the JohnBar function. And so we just separate the argument with a comma. We say the color is equal to, and handily we can just type black in quotation marks and hit Control Enter. And that looks a little bit neater for us. Now, it's rare that we would get away with just plotting the mean of the results of our experiment without showing some indication of the variability or of actually showing the raw data itself. I am not a fan of dynamite plunger plots, as they're called, where you sort of have the bar at the mean and then you have the top half of an error bar sticking out to give some indication as to the variability in your data. Because I think that they don't actually convey the distribution of your data well at all. You can have many different distributions of data that fit the same mean and standard deviation or standard error pattern, and it's also not a great way of showing quickly the number of observations that you have in your experiment. And what it is good at is hiding poor data, such as data that is scant or is non-normally distributed. And so I would argue actually that most of the time, in most situations, you can create efficient and attractive plots, plotting the actual individual replicates themselves. And so if we want to add the dots to represent each individual data value on top of our bars, we again just refer to the sort of ggplot mantra, the grammar of graphics, and we can simply add things on top as an additional layer using the plus sign. And so we're going to go back to the John point aesthetic as we added earlier on. And now if we run this in whole code, we get the plotting environment with the ticks and the axis names, etc. We get the bars at the mean as we drew them. And then on top of that, we have layered our data points to represent each of our individual observations. Now, this isn't particularly attractive, and it's not particularly easy to look at or to work out the distribution of our data, because all of these points in a straight line are sort of all on top of each other. They're quite small. It's not particularly easy to differentiate one from the other. And so there are a few things that we can do to improve this. If you've come from plotting using Prism, you'll know that often if you have a lot of data points, Prism will, or you can ask Prism to what's called jitter your points. So their value on the x-axis stays the same, but they slightly vary their position along the x-axis to separate the points a little bit better so that you can get a better understanding of how the points are distributed. We can do this in ggplot as well by inside actually let's copy and paste this again. Inside the John point function, we're going to supply the argument position, and we're going to say that we want each point to take on position jitter. And let's see what happens when we run this. Okay, so that's sort of an improvement in that now each individual point has been separated so that you can see each point and it's not overlapping with anything else. But it looks a little bit ugly because of the way that the points are separated. The points are separated basically the same width almost as the width of each bar. It doesn't really look very great. But we can control the width of the jitter of our points to make them a little bit more aesthetically pleasing. And we can do that by supplying the argument inside the PositionJitter function. So if we have PositionJitter equal to 0, all of the points are perfectly lined up with each other. If we have PositionJitter equal to 1, well, that's not great, is it? Because the jitter is in fact wider than the width of the bar itself, and we can't really tell where the data from one bar starts and where the other one finishes. Let's try a position of 0.5, somewhere in the middle. Okay, that's still not great, still overlapping. Perhaps 0.2. That's a little bit better. Still not the most attractive plot in the world. There are some improvements that we can make to it. For example, let's increase the size of each point. Let's say each size equal to 5. Perhaps that's a little bit too big. Let's try size 3, and let's try a different shape. Let's try shape 21. Okay, that's perhaps a little bit nicer. Have a play around with the different shapes that you can use. You can find out which shapes correspond to which number by going to this website. Is an example, or a quick Google will show you basically the different numbers that correspond to the different shapes that you can manipulate. The major difference between shape 21 and the shape the circle that we initially started with is that 21 you can control both the fill and the color, which is the border. Now, same with any other function in R. You can save the result of the function to an object. So let's call this my plot. Use the assignment operator, and then if we call my plot, then R calls all of this code and produces our plot for us. Now, we've been able to create our plot. We've mapped our variables to lots of different aesthetic mappings. Perhaps we're pretty happy with sort of how the plot looks, but we want more control over some aspects of the plot purely based on our taste, or perhaps it's restrictions imposed by your supervisor or by the journal that you're publishing in. Perhaps you want to change things like the background color, whether you have grid lines or not, whether you have a border, the size of the text, etc. And you can do that using the theme command. And just like layering on top different geometric objects, you can layer on top different theme options. We'll see how this works in a second. So carrying on with the myPlot object that we've just created, as this is a ggplot object, you can just add additional things to it like we did before with the plus operator. And so to this, we're going to change the theme of our plot. So we're going to use the theme function. And we're going to do a few things. So we want to get rid of the grid lines. We want to change the color of the background. And we want to add black lines to denote the X and Y axes. So let's remove the grid lines. Panel grid equals element blank function. Let's just run this and see what happens. So you can see now that the grid lines have gone. We're just left with a plain grey background. If you type, let's do this here. If you type question mark and theme, remember this is just how we find help for a particular function, and hit Control Enter. In our help viewer, you see that for this theme function, there are a huge number of arguments that we can use to control different elements of our plot. You can see them listed here. So axis title Y, axis ticks, all these things that you can change about your plot to make the plot conform to however it is that you want it to look. Change things about the legend, about captions and subtitles, etc. So consult this help to see exactly what it is that you can change to improve about your plot. And also there's a wealth of information online if you want to change a particular aspect of your plot. A quick Google will often find that there's someone online that can has already asked, and you can find out how to do that. So we layered on top of our plot object a theme option, and inside this theme function we identified the aspect of the plot that we wanted to change. so the panel grid, all of the grid lines. If we wanted to, we could have selected just the X or just the Y grid lines, but panel grid selects all of them. We've said is equal to, and then we basically told it to become blank. That's what this element blank function does. It says just remove it. We don't want to see it anymore. We can add additional arguments to this theme function. We can separate them with a comma, and just to make things easier to read, let's separate them onto a new line as well. We want the background of the plot to be white instead of a grey box, and so we use the argument panel.background. It's equal to, and now the background, I hope you can see, is basically constructed out of a rectangle, and so we use this function element rectangle to allow us to change the options of the rectangle. So it has a fill and of course an outline. Well, at present we don't have an outline, but we can say that the fill of this rectangle is equal to white. Again, if we run this now, it removes the grey box. But one thing that the grey box did serve to do is tell us sort of where the x-axis and the y-axis end, and now we no longer have that. And so we might want to have a vertical line here along the y-axis and a horizontal one along the x-axis. Again, we use a comma so that we're adding an additional argument. And the argument that we're going to add is axis.line.y. So this is going to add an axis line against the y-axis. This is instead of being a rectangle, this time is element line, which allows us to control the aspects of the line. The color is black, and the size of the line, which controls the weight or the thickness of the line, is going to be 0.2. Oops. I tried to cheat. I think we actually need to supply the word color in full. Yes. And so now you can see that we've got this nice y-axis line, but we could probably do with one for our x-axis as well. So I hope that you can see that we can repeat this. If we just copy and paste this, add a comma, new line, and let's just edit this so that it says axis line dot x. And run. And now we have our plot with no background, no grid lines, but a line against the y-axis and against the x-axis. Now I quite like having my plots sort of encapsulated inside a box, or having a border all of the way around my plot. And you can do this by, if we replace these two and say we want panel.border, which is a rectangle. So this is the border that goes all the way around our plot. The color should be black, and the size, let's say fill equals NA, because we don't want it to be filled in, and the size equals 0.2. And so if we run this, then we get a similar result with our x and y axis, but now we have a box that goes all the way around our plot to sort of properly demarcate exactly where our plot finishes and where another one might begin. Now, it might seem like quite a lot of work to achieve the look of a plot exactly as you want it, especially if you particularly dislike the default appearance of plots produced in ggplot. And so handily, ggplot comes with a number of pre-built themes which you can apply to your plots. And although they may not represent or give you the result exactly as you want, if you find the one that matches most closely the result that you want, then it may only take a couple of tweaks to get the plot exactly as you want it. And so if we take my plot, there are lots of themes that come pre-built. So actually, let's just remind ourselves of what the base plot looks like that we created earlier. So that's the default. And on top of this, ggplot comes with themes such as theme black and white. And again, note that these are all functions. and that looks reasonably similar to what we had earlier, except we have grid lines in there. There's another theme, theme classic, which looks similar to what we did before we had the grid. There's quite a few of these. I'm going to go through them one by one so that you can see exactly what they all look like, and perhaps decide for yourself which ones you would prefer to use for your own plots. Oops. And you can, if you find a theme that you like, so I quite like this theme line draw, then you can add your own theme argument after you've applied the theme template, and change an aspect that you want. So, for example, we could say panel background equals element rect, and let's change the fill to something garish like blue, which is a horrific plot, but hopefully you can see that what we've done is created the plot with the default appearance. We've applied the line draw theme, and then on top of that, we've layered this additional option that I've added, which tells ggplot to make the background of the panel a rectangle that's blue. Okay. Now, often if you have a project that's ongoing, or perhaps if you're writing your thesis or for a paper, generally we like our plots to all be of a similar kind of theme, to have the same color theme, or the same sort of grid lines, or the same width axes, etc. And so what I find useful is to define your own theme as you like it once, and then you can apply that theme to all of the rest of your plots. So, for example, I have a theme called theme Hivin, which I've defined before, which you can see I've changed quite a lot of options. You don't necessarily need to change this many, but over a long period of time I've created this theme as I want it, and instead of having to type this out in every single analysis or experiment that I do, I simply save the result of this theme function to an object that I've called theme Hivin, and let's run this, and then all I have to do is type my plot, add theme Hivin. Note here that this isn't a function, this is an object that I'm applying, but the object evaluates to this theme function. So, for example, this would be incorrect. But if I run this, then I get a plot which has had the theme aspects altered to the definition in my theme object. So you can see, well, not that much has changed from the base, except that notably you can see that the axis values are much larger, and so are the axis labels. And so this is a useful way of defining a theme once and applying it to all of the plots for a project or a thesis. And handily, if I decide that actually I want to make a change to my theme, rather than having to change every single plot or experiment like you would if you were using Prism, all I have to do is change something in this theme file, and then just rerun my code, and it'll update that change in each of the plots that are dependent on this theme. Now, before we move on to the finishing touches, changing axis labels and titles, etc., I mentioned that we'd talk about using box plots quickly. So if we copy this section of code here and paste it down here, I've skipped ahead a little bit. The geometric object for creating box plots is handily JohnBoxPlot. And let's just apply this with just these options. So we've specified the fill and the color as well. And so we get lovely box plots with the 5 summary statistics. So you get the median, the upper quarter, the lower quarter, the Tukey max and Tukey min for each value. And there's an additional argument which you can add to the box plot, which is notch equals, so by default this is false. If you add true, you get these notches, which represents the 95% confidence interval for the median. So the range between these 2 points, between these 2 points is the confidence interval around the median. And note that because our John point layer is still here, then the points are layered on top, although we haven't jittered them around as we did before. Another thing to note is that remember that we are layering things on top of other things, and so if we were to swap these around, then this happens. So note now that the boxes are on top of the points, because literally what happens is the base plotting environment is drawn, the point geometric objects are drawn, and then the box plot geometric object is drawn on top. So if you find that your points are disappearing behind different geometric objects, check the order that you've supplied things in. So we've got a plot that we're reasonably happy with. Actually, let's go back to this plot. We've got a plot that we're reasonably happy with. We want to apply the finishing touches. So we want to change the axis labels and add a title. So let's call this finishing touches. And let's steal this from up here. Let's stick with our putting things on a new line. Oops. So we want to change the axis labels so that they contain a little bit more information and look a little bit nicer. So we use this using the labs function. X. Well, on the x-axis, actually, it's reasonably obvious. Often, if you have a factor mapped to the x-axis with different categorical levels, exactly what we have mapped. So I think that having species here is a little bit simplest to requirements. So there are a couple of ways that we can remove it. We can remove it actually using a theme option by telling it that we want the axis title x equal to element blank, but a slightly easier way of doing it is simply saying that we want the x-axis label to be equal to nothing. So this is a character string with nothing in it, and so that will remove the x-axis label for us. For the y-axis, we want the label to contain a little bit more information, and so this is going to be sepal length, and of course we were all taught as undergrads to always include the units for our axis labels, and so these the sepal length is measured in millimeters. And so if we run this, then we find that this label species has gone because it's quite obvious what these are. And now we've got this nice, much more informative y-axis label of sepal length in millimeters. Now, we were always also taught in undergrad that a good plot should have a title. I know often we don't adhere to this anymore, but if you do want to add a title to your plot, we do this by adding the function ggtitle. And our title is going to be sepal length by iris species. So that looks pretty good. Sometimes you may want your plot title left aligned, which it is by default, but also conceivably you'd quite like your title to be in the middle of your plot. And we can control this using the theme function, which again you can use to control virtually anything that is customizing your plot to your taste. So let's add a theme layer. And the argument that we want is plot title. And this is equal to element text, because we're changing an element which is text. And there's this funny little argument called hjust, which is a horizontal justification or horizontal adjust. And if we set this to 0.5, then we find that our plot title is put in the middle of our plot, which is a little bit more desirable here. So we're happy with our plot. We're ready to save this to put in our lab book or in our thesis or send to the journal. And there are a couple of ways of doing it, some of which are better than others. So let's call this saving our plot. So in RStudio, you might be tempted to click on this export button, which you can use to either save as a PDF or one of many image files. So let's click on image. You can choose whether to save as a PNG, JPEG, TIFF, etc. Even an SVG, which is useful. You can define where you're going to save your image and give it a name. And you can customize the height and width here, which is in pixels, I believe. I prefer not to do it this way, basically because sort of the how you the pixel values for changing the height and width basically depend on how you've shaped your window, how you've adjusted your window like this will affect the numbers that go in here. And although you can specify exactly what you want them to be, I can't really think in pixels as easily as I can think in centimeters or inches. And so I think the best way to save your plots and at the same time specify their dimensions in sort of a more easily understandable dimension is by using this function called ggsave, which saves the last plot that you produced with a file name that you specify in a format that you specify and with the dimensions that you specify. Before we go on, I should mention that at the moment we haven't set our working directory, which you'll remember from the introduction to R workshops is quite important. And generally the way that I prefer to do this is by setting a project. Remember up here, by creating a new project and then working from a project file. But actually for this, I'm just going to show you the other way of doing it. Just because if we create a new project file now, we'll lose the work that we've already done. And we can do this using the set working directory function. And then you just specify with within quotes a string for the path where you want your files to be saved. So for convenience, you could just set this as your desktop. I'm just going to set this to my documents, and then if you Control Enter, then you've set your working directory. So this ggsave is going to save the most recent plot that we've created, which is this one. Note that it's not necessarily the plot that you have currently open. So for example, this is the most recent plot we've created. I could change it to this plot. This function won't save this plot just because it's open. It will only save the most recent plot that we've created. So we're going to call this something unimaginative, goes in quotes, graph 1. And the file format, so ggsave is quite intelligent in that the file format that it will save depends on the file extension that you supply. So .pdf will of course save a PDF file. We can do .png for a PNG file. If you're using Windows, sorry, a slight aside. If you're using Windows, the PNG files may not always come out as sharp as they would if you're using a Mac or a Linux. And there's an additional argument that you can supply, which is type equals Cairo dash PNG, which will make your plots slightly more high resolution. As well as PNG, you can supply them as you can do SVG files, scalable vector graphics, if you're using something like Illustrator or Inkscape, which is useful if you want to create more complicated figures from these. For this to work, you may need to install a package called SVG Lite for that one to work. But for now, we're going to save this as a PDF. We want the width to be 8. This is in inches, and the height to be equal to 5. If you want to specify the inches, then you can say unit equals inches or centimeters, depending on what you want. But by default, it's in inches. And if we run this, then we find our graph. Now, before we finish, there's one additional thing I want to show, which is going to be quite useful, I think, for the kind of plotting that most of us will be doing, which is when we have factorial data. So, for example, we may want to plot 2 different color bars for each of these 3 levels. So perhaps we had wild versus captive for each species, for example, just because there are a couple of additional things that we'll need to know. So to do this, we're going to load in a new example dataset with the data command, and this dataset is called tooth growth. And if we just have a quick look at our new data table using the head command, we can see that it's a data table of 3 variables of len, presumably tooth length, sup, presumably for supplement, and dose. I don't know much about this data set, about exactly whose teeth we're measuring or what they were supplemented with, but it serves to demonstrate this purpose. Because if we look at the summary of this data set, we'll see that our length variable is a continuous variable. R R thinks that dose is a continuous variable, but actually we have a value of 0.5, of 1, and of 2. So actually this is we could take this as being either an ordinal or categorical variable. And then supplement is a categorical variable with 2 levels, each with 30 observations. Basically, whose ever teeth we're measuring, we're given either OJ across 3 different doses, 0.5, 1, and 2, or we're given VC across 3 different doses, 0.5, 1, and 2. And so this is a factorial design experiment. So let's plot the data as such. So if we use our ggplot function, the data is called tooth growth. We're going to map, we're going to map the supplement on the x-axis, length on the len on the y-axis, And we're going to plot these with bars, and we want the fill of the bars to be mapped to dose. And now we're going to add JohnBar, and we want our bars to be plotted at, let's say we want them to be plotted at the median of each group. So remember, we have to say that the statistic is a summary statistic rather than being count, and that the statistic, the function at y, is going to be median instead of mean, like last time. And then let's say that the color is going to be black, so that we get a nice border around our bars. Now if we run this isn't quite going to look how we want it to. So instead we've just got a single bar for each that are both grey. They haven't actually been filled by dose. The reason that is because, well, one of the reasons is that R has seen dose and has decided that dose is a continuous variable, and therefore it's deemed it inappropriate to draw a separate bar for every single value of dose. And so instead we need to tell R that actually it's got it wrong and that dose is a factor. And we can do that with the handy as.factor function, which basically tells R to treat dose as a factor. And so if we run this, it still won't look quite as we expect. So as you can see, instead of what we're aiming for, which is 3 separate bars within OJ and 3 separate bars within VC, instead the data are stacked, which is the default position for JohnBar. And we can change this with the position command argument. And there are a few options that we can use for this. One of them is stacked. Oh, sorry, not stacked. It's just stack, which is what we had a second ago. Another option is fill. And now the difference between stack and fill is that whereas stack just stacks the mean of each bar on top of the mean of the other bar, what fill does is take the 100% within each group and plots the width of the bar as the proportion that each dose takes up of this. So you can see that the mean of the length variable was higher in subjects treated with the high dose VC compared to the high dose OJ. This is useful if you're comparing proportions between different groups, but actually in this setting it's quite difficult to interpret. That's not really what we want. The position that we want is dodge. And if we run this now, that's a lot more like what we're aiming for. So we have 3 bars within OJ, we have 3 bars within VC, and it's much easier for us to compare these different groups and to compare the relationship with doses. Now, one final thing to add on top of this is that you'll get you need to adjust the position of whatever other geometric objects that you add as well. So, for example, if I just add John point on top of this isn't quite going to look how we want. So you can see that all of the data points for the OJ and the VC have just been plotted in the very center of these 2 groups, which isn't quite what we want. And so we need to specify position equals. And if we do dodge, ggplot doesn't like it. And for John point, we actually have to specify exactly how much to dodge by. And if we set this to 0.9, then we find that the data points dodge correctly into the same position of the bars. The reason that you don't need to specify position dodge for the bars is because basically the default here is to dodge so that the edge of one bar touches the edge of another bar. There's a variation on this graph that we can make using a line geometric object, which we've not used before. So if we create a new plot, growth, aesthetic mappings, this time on the x, we're going to put as factor dose. On the y, again, we're going to have len. And this time we're going to group by supplement. And we're going to add JohnLine. And you can see that this result is a little bit strange. And the reason is that just like JohnBar, we need to tell JohnLine that we want it to plot summary statistics, and that the function we want it to plot is the mean. And so what's happened is by supplying this group aesthetic, the line geometry has produced a separate line for each value of the supplement variable. So we've got a line for, although actually at the moment we can't tell which is which, and the reason is that we haven't supplied an aesthetic mapping such as color. So let's go ahead and do that and say that color also equals supplement. And if we repeat this, then the lines are colored and we get this legend, so that now we know that the red line is the OJ supplement and VC is the and the green line is the VC supplement. There's one very last geometric object that I want to show you, which is John Smooth. And what this does is draws regression lines onto our plots. Now they could be, depending on how we set this up, they can be linear regression lines, they can be non-linear regression lines, or they can be low S or splines to sort of fit the trend of our data. By default, it uses low S lines, which, I mean, here we only have 3 data points, but you can see that it plots confidence intervals. And we can change this by specifying method equals, for example, if we want a linear regression line, LM, if we do this, we should get linear regression lines where, because we've layered this on top, we still have the John lines. You can see the thin line that kinks in the background. But we also have, because of this, our fatter linear regression lines with their confidence intervals around them. The same with anything in R. Playing around with it yourself is the best way to learn. So use what we've learned in this video tutorial to try and plot your own data, find solutions to problems. ggplot can take a little bit of getting used to, and sometimes you come across a problem that you find difficult to solve at first, but there's plenty of information online and help online for doing different things, so please consult Google and have fun plotting your data.